Okay, now it's recorded. Okay. Okay, so last time we are dealing with the squeeze theorem. Okay, so every time you have three functions, okay, you have f, g, h, and when you have the functions, okay, all getting in, having an intersection at one point, at least one point, okay, you can have, okay, if you know the limit, okay, of your first functions and limit of your third functions, then you can conclude the middle functions will be the same, okay, the same L. Okay, we go here, try to prove limit as theta getting 0, sine theta over theta is 1. Okay, so in the first method here, we are comparing BC, AB, and the arc AB, the curved one. Okay? So straight line BC, straight line AB, and the curve AB. We try to find any relation between all of those lines by making angle from this OA, OB, the length, the angle theta, and we just make fixed radius 1. Okay. So we are making sine relations and tangent relations for the AE. And then we make some conclusion here. Okay. So we can include the tangent. Okay. And we can conclude from the first conclusion and the second conclusion using tangent. Okay. So you can have, okay, you switch the theta and cosine. So you can have cosine less than sine over theta less than 1. So you can see here, okay, it's actually cosine as theta getting 0 is 1, and then limit of 1 is 1. So the middle one should be 1. The middle function sine theta over theta is 1 based on our squeeze theorem. Okay, this is if we using comparison online. Okay, we can also use another approach. Okay, this is, I call this the comparison of area. Okay, if you think my words or the writing is too small, please tell me. Okay, if it is too small, then I need to make it bigger. Okay, so let's consider OBOA here, triangle OBA. Okay, so consider, so the area for this triangle is, you have a height here. So the area will be half OA BC, right? Okay. And the other part, okay, the area like a pizza, right? We call it the sector. If you don't know the name of the shape, this is called sector. Okay? The one whose shape is like a pizza slice. So this is O, also OAB. Okay. This is theta. Okay. How about area of the sector? Anyone remember how to find the area of sector? Anyone? Anyone remember? Area of the sector? So you have a slice of pizza, right? Can you calculate the area if you know the angle and you know the radius? Can you calculate? Remember? Okay. So we need to have a ratio of the theta, the angle theta, and all angle of the circle, 2 pi, right? Circle is 2 pi. Okay. So theta over 2 pi is multiplied by the area of circle, right? So we have, because our radius is only 1 from our definition from the beginning, so we just have half theta, right? And here is also area for OAB is half. OA is the radius, is 1. BC, we can approach BC from the sine. So I will write here, sine theta is BC over OB. But because OB is 1, so sine theta is BC, right? Okay. So I can write this is 1 and sine theta. And then the third part, let's consider this okay, this triangle. Maybe I will make it okay. Okay, that big triangle OAE. Okay. If you see here, all of this triangle also at least having 1 point for B, right? And also A. So area of this for triangle OAE, okay, this is half OA and AE. Okay. AE, if you remember from previous, we have tangent theta is AE over OA. Because OA is 1, so it's equal AE. Okay. So we can have our area is half of tangent theta. So first is half of sine theta. That's for OAB. And then for the sector is half theta. And for the OAE triangle, it's half tangent theta. Okay. We have 3 functions now. This is our functions area. Okay. So we are using all these 3 area as our functions. I will make it from here. This is half sine theta. This area for OAB. This is sector. And this is area for OAE. Okay. Okay, is it too small or behind? It's okay? Okay. Oh, by the way, if you want to check later, your notes and my notes. I will upload the PDF file. Hopefully, we can finish the chapter 2 today, and I will upload the PDF file until the last chapter here. Okay, I will go for the next slide. Okay, so we have triangle OAB. Okay, it's of course it's less. Okay, it's less. Let's say it's less or equal. It depends on the function. Sector OAB, and then it's less than triangle OAE. Okay. So if you see one more time from here, of course, okay, OAB, the triangle, it's less, okay, it's less than OAB for the sector, and it's the larger triangle is the bigger, right? The biggest one. Okay. So from the shape, you can see that our comparison here is true. Okay. So OAB is half, or I will write sine theta. I'm making this absolute value is just to make sure that all of our calculation is positive. Okay? Because we are comparing the positive numbers. Okay, we are not including any negative, but this is just to make sure that all is positive. The sector is theta over 2. This is tangent theta over 2. Okay. Okay. First, let's multiply all by 1 over sine theta. So you will have half, or let's just cancel 2, okay? And then this become 1. Tangent is sine over cos, so it will be 1 over cos. Okay. And then because our goal is to find this, right? Which is in the middle, but it's flipped, right? So we need to flip the middle one. So we flip, then it becomes this. Okay. And then we're just using our limit, or let me so limit theta getting 0, limit theta closer to 0, limit theta is closer to 0. This is just 1, it's a constant. Let me write limit as theta getting 0 of cos 0 is 1, right? So it's 1. So based on Squeeze theorem, limit as theta getting 0 of sine theta over theta is 1. Okay. Okay, any questions? Personally, I prefer this proof compared with the previous proof, okay? Because it's more easy to observe. Okay? The triangle shape and the sector shape. It's easy to prove. Okay? So you can have two approach. You can have the line and the line approach, the straight line and the curve, and you can approach with the area of a triangle. Okay, at least from here, you know how to use the squeeze theorem. Okay? If you have any problem and you don't really know the function is, you can approach the functions. Okay, you can approach with geometry from the area, from shape, maybe later volume, etc. But I think for calculus 1, you need to focus on only area, two-dimensional area. The volume is only in the integrations, but later then. Okay. But for squeeze theorem, you can approach with any functions that you can find. You can model the problem. You can model into functions and make three functions. Make sure the first and the third one, you know the limit value. And when you know the limit value, you can approach the middle functions. Okay. Okay, so because we already proved the sine x over x, okay, because we already proved sine x over x, so every time you see any limit problem, whenever you see, okay, this sine x over x, okay, x is closer to 0, then you can always answer that this is 1. Okay? So when you have trigonometric complex equations, you simplify the form and you find this sine x over x. And you can just conclude, oh, it is 1. Okay? Like for example, if you have limit x to 0, this is 1 minus cosine x over x. Okay, I will solve this. Okay. So first, I will write this as a function. And then I will multiply by the opposite sign. So why I'm doing this multiplication is I want to change the top one through some identity in trigonometry. So it will be 1, okay? And the bottom one is, I will just keep x, 1 plus cos x. Okay. So here it will be sine squared x, and the bottom one will be x and 1 plus cosine x. Okay. And here you can separate this. Okay. So you can separate. Okay. So later in any problems in any exercise, you can manipulate any trigonometric using identity. And when you define sine x over x, you can directly go, this is equal 1. So this is equal 1. And this is equal, this is becomes 0 over 1 plus 2, right? So it's 0. And the total is 0. Okay, that's just example. Okay, you may find more examples later on. Okay, maybe in your TA class, or maybe if I have time to review and having some exercise with you, I will show you some problems. Today's session, I will focus on, we call a precise definition of limit. Okay, maybe you've heard before in high school. Okay? Maybe some not. That that is okay. Or usually it's also called by delta and epsilon definition. So what is delta? What is epsilon? So let me explain to you. Okay. Okay. So here from this part, multiply by the opposite signs, you get the identity for 1 minus cos squared. It becomes sine squared. Then you separate the functions. Sine squared becomes sine. Okay. Then the left part is 1. The right part is 0. Okay. Actually, for evaluating the limit, we have also another rule. It's called L'Hopital rule. In some way, it maybe it will be easier, but in another problem, you just need to just factoring or just rationalizing or just using identity. Okay. Any method in algebra you choose depends on you, which one you prefer. You want to solve the limit first by maybe factoring, or maybe later, if you know the L'Hopital rule, you can solve by L'Hopital rule. But I'm not touching L'Hopital rule now. I will focus on the factoring, rationalizing, and the trigonometric identity. Okay. Okay. So next page, I will focus on what we call precise definition. This is the definition. I will just write def. Okay. Precise definition of limit. Or you may call this epsilon delta definition. Okay. You have a limit. Okay. Maybe like this limit. Let's say this is A. This is L. Okay. From our limit concept. Okay. Okay. So from our limit concept. Okay. When you have this kind of graph, you have the functions. The blue one is your functions, and you have a hole. Okay. In the middle of the function, you have a hole like in the middle. Okay. When you approach limit, okay, as x approaching a of your functions, when you have this case, okay, you have the limit, right? It's L. Okay. But then there's another question. Okay. We know that it is the limit is L. Okay. But actually, how close? Okay. How close the limit? Okay. Because limit means we are getting closer, 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 right? But how close? That number, how close we are to the limit, is what we call the precise definition. So that's why we call it precise. So we need to know how close we are to the limit. Okay? That we need to find relations. Okay, so let me write here. Let me draw in this interval here, nearby A. Okay? Imagine this red color is really, really small. Okay? Imagine it's really, really small, maybe at 0.00 something, maybe. Okay? But to illustrate, I will just draw this red line here. So delta is the distance between A and the closer one. So here is A, so A minus delta here. And here's A plus delta. So delta is distance between some number to A. Because of this distance, it's also affected the value of the functions, or in this case, the limit, right? Okay. And epsilon is the distance between L and some value. Okay. So L plus epsilon, and this is minus epsilon here. So you can have the interval is here, around here. Okay. When you are moving your x, you are moving your delta, it will change your epsilon, right? When you move the delta going to the far left, your epsilon is going down, right? When you are moving to the right, it's going up, of course, right? It will affect the value. Okay. So we can relate, there is a relation between delta and epsilon. Okay. Let me write some words. You may take a note on, or it doesn't really necessary as long as you understand what does it mean. So let the function define or I can skip this one. This is just regular limit definitions. I will just go for if, okay, for every epsilon greater than 0, there is, okay, a number such delta that if this is very formal words, very formal definition, I'm encouraging you not to memorize. Okay, don't memorize. Don't. It's bad for you. You just need to understand the logic. So if, okay, so if your distance x minus a, okay, is less than delta, then your functions minus L is less than epsilon. Okay. That is what we can relate from the graph. So when you are moving your delta, your epsilon is going to change. Okay. So every distance, delta distance, you will change the epsilon. Okay. 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 So this section is somewhat weird, confusing at the beginning. Also, I must confess to you, in my undergraduate, I also don't understand this stuff. Okay? But I try to get you more in line with our subject here. Okay? So we are actually, what we need to do is we need to find delta epsilon relations. Okay? So the problem will be you have a functions, you have the limit of the functions, you have the number, and you need to prove that limit is true. So how to prove that? Based on our definition, we need to relate, okay, this distance x minus a delta and relate with the fx minus l epsilon. Okay, so we have the limit, right? So this is the distance, right? X closer to a, this is the distance of x minus a. And this fx equals L here is our epsilon, right? This is f. So we need to take some approach how to relate the distance and of the delta and the epsilon. Okay, I will just showing you what does it really mean. Okay, let me show you another illustration so that you will having more understanding. So you have any functions here. Let's say you have 7 and maybe 4. So you have a closed number here. So this is also your closed number. So for the x-axis, that's delta. For the y is the epsilon. So this is 7 plus delta. It's 7 minus delta. 4 minus epsilon, 4 plus epsilon. Okay, for example, okay, your distance. So I will write this is limit as x approaching 7 of your function is 4. Okay? From the definition of limit, that's 4. So, for example, if delta is a small distance, and assuming some fixed number, assuming maybe here we try 0.01. So this is just illustration. Okay, this is just illustration. So your distance is between 0.001 and minus 0.001. So your actual so maybe here, okay. So this is if we assume delta is 0.01. So any number so any number having this interval, they are all true. Okay, they're all true for the these equations. Okay, this is just illustration. Okay, to show you that what we are dealing is a really small number. Okay, maybe still confused. I will go to the direct problem. Okay, direct problem of this precise definition of limit. So, proof limit as x approaching 4, 2x plus 3 is 11. If you are just if we close the answer here, of course, okay. If you need to evaluate limit, first you substitute, right? Direct substitute. Put 4 to x, it becomes 8 plus 3, it's 11, right? Of course, it's 11. But the question is how to prove that. If we try to solve it, a proof by using a precise definition of limit. So how to prove that? So to prove that, first we write given the epsilon greater than 0, delta greater than 0, meaning what we need to prove, actually, we need to find and relate delta and epsilon. Okay. How we are going to do that? First, let's see here. This is our A, right? This is our function. And this is our L. Okay. So first, the definition start by if, okay, let's try x minus 4 is less than delta. Then let me just write the fx minus L. So fx minus 11 here, the L. This is all less than epsilon. Okay. First, this is the original equation from the questions. Okay. So what we are really doing now, we need to relate this delta, and maybe it has some relation with the epsilon. So first part is called, we need to finding the delta. Finding delta to prove our equations. Okay? So we start from the epsilon. Okay? We start from the epsilon to find delta. So let me simplify the form. I can write this as 2x minus 8, right? As you can see, you can if you're familiar, 2x minus 8 is twice as x minus 4. I think we can have some relations there, right? So we can have 2 x minus 4 is less than epsilon, right? So x minus 4 is less than epsilon over 2. At least we get this idea, okay? Because the function is only linear, it's simple, right? Simple functions. So we can get the idea that, okay, so assume, or let's let the delta is equal epsilon over 2. So we find delta, which has relation with epsilon, epsilon over 2. Then the second part, so this is the first part. So the second part is the proving delta. So proving delta, we start from x minus 4 less than delta. And we substitute delta with epsilon over 2. Then we can start to see it will bring back the original equation. I will write this is as 2x plus 3 minus 11. This is all less than epsilon, which is true. Okay. Then we can write as when delta is epsilon over 2, we can write this f of x minus L is less than epsilon. That's how we prove that the statement of the limit is true. Okay. So we find the delta. So it's like we move forward and we go backward, back to the original equations. That's how we prove equations using the delta and epsilon. Okay. So it's not necessarily to like evaluate limit, find numbers, right? You find the final answers. There is no final answers here. This is all proving that the limits are correct based on definition of delta and epsilon. You may find this is weird, strange at the very beginning, but when you understand the concept, you will see that, okay, that's actually makes sense. Okay. Okay, for linear functions, I think it's quite simple. It's not really that difficult. The difficult part maybe when you have maybe quadratic. You have quadratic function and you need to prove the quadratic function is correct. I will give you one more example for how to use the precise definition, and we go to the next section. Okay, any questions for online students? Any questions? Any questions so far? Okay, any questions? Confused? 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 No? Okay, understand? Or you can write the proof symbols, the QED, but it's not necessary. Or you can write the full equations, this equation here. You can write again here. Okay. Okay. Okay, we go to the next one. Or you still want to write the notes? I will give you a couple of minutes. Okay. Or do you want to try? Whether you want to solve the proof. Do you want to see the last page or enough? Okay. Don't worry. I will upload the notes later. Okay. Okay. Proof this limit. Proof by precise definition of limit. Okay. If you want to try, you can try. But first, usually if we want to prove something, we need to write all the given information or given assumption. So let's just make the epsilon is greater than 0, and then need to find, or this is just to remind you, need to find delta greater than 0. Okay. So this is A, this is f of x, this is L. So first we have the f of x minus L less than epsilon. We can go directly just solving the epsilon first and then later go to the delta. Or if you want to write the delta, you can write delta. Yeah. So all the functions will be x squared minus 4x plus 5. Okay. And then minus 1, the L. It's less than epsilon. Okay, we may need to solve this problem first. Okay. So it will be x squared minus 4x plus 4. It's less than epsilon. I think we can factor it. Right? Yeah. And then maybe we may have this kind of expression, so we can square both sides here. Because it's always positive, we only consider the positive epsilon. Okay? Then we have these relations. So this part is find delta. So we can let the delta is equaling square root of epsilon. And then we need to show that when you have the x minus 2 less than delta, and because we are using the delta is square root of epsilon, this is less than square root of epsilon. And we need to try to solve and try to bring back the original equations. going back to the questions. So squared both sides. Okay. And we can make it back to really close to original equations. So by delta equaling square root of epsilon, so it's proven that this is the long words. You can write it or just stop here. It's okay. The previous one is also you can write the long words like the conclusion or just stop there because it's already proven. Yeah, this quadratic function is also not really that difficult because it's you may have see the epsilon and delta right away from the squaring, right? From the squaring both sides, you see it's square root of epsilon right away, right? But what if you have two factors, like for example x minus 2 x plus 3? What will happen? You may have the x plus 3 go down, right? I will explain to you. Have you learned the epsilon delta in high school before? Have you learned before in high school? High school? No? No, right? No. Okay, this is how to prove. Okay, the problem is arising when you have, for example, you have a limit okay, proved by precise definition of limit. Let me write all the necessary steps at the beginning. Okay. So let the epsilon greater than 0, delta is greater than 0, so that your x okay. Now we may start from the epsilon. So x squared minus 9 is less than epsilon. We try to factorize this. We factorize x plus 3, x minus 3, right? And then what is happening now? Your expression become x minus 3 less than epsilon x plus 3. Okay, I will write question marks here. So this is important, okay? So delta, I will write notes here. Okay. So notes delta, it need to be only depend, or I will write depend only with epsilon. Okay, and I will write here, it cannot depend on x. Okay, so when you are approaching the epsilon like this this case, okay, so x, the distance of x minus 3 less than epsilon over x plus 3, you have x also here. Okay? In our definition of limit, in precise definition of limit, okay, we need to remove this x plus 3. We try to remove, okay, because the delta, it should be only with epsilon. So there should be not any x in this epsilon equation. So we need to remove the x. Okay, any idea how we are going to remove the x plus 3? How to remove that? Okay, we are not going to use any algebra operations to manipulate the form. No, we are going to assume as long as our assumption is correct. Okay, we are going to assume. For example, in math, proving with assumptions is fine. It's fine. It's okay if you can prove the assumption is correct later. So we can assume anything at the beginning. So we assume now, okay, we assume this x minus 3, the distance, okay, it's really small. First, that is our assumption. Of course, based on our previous slides, it's really small. But how small? Okay, I'm just going to draw the same illustration. So 3, this is 3 plus delta, 3 minus delta. Okay, delta is small. First, okay, wait a moment. Let me, okay. Let me connect the presentation. Okay, so back to our equation. So we need to assume, okay, assume, okay, you can assume the x minus 3, okay. You can assume with any small number you want, 0 0.1, 0 0.2, any number. But to make the calculation easy, just assume that the distance is smaller than 1. You just use 1. It's easy number. Okay? Small is 1 here. Then your inequality will be -1 less than x minus 3 less than 1. Okay? So you can solve this limit at plus 6. Okay, all the number here, because I want to make out x plus 3 from x minus 3. Okay, okay, so this becomes 5 less x plus 3 less than 7. Okay, let me reciprocate all, and then to make it all using the less symbol, so 1 over 7 less 1 over x plus 3 less than 1 over 5, and multiply all by epsilon. So we'll have epsilon over 7 less than 1 over x plus 3 epsilon less than epsilon over 5. Okay. So from this inequality, okay, at least you can have the minimum value, the minimum number, the minimum epsilon here, or the minimum delta is here, epsilon over 7, right? So what we are going to do is, so this is find the delta and then proving. So let epsilon to the 0, and the delta is, we are using the delta minimum from this interval. Because the largest amount of value is 7, or you can also use 1 because that is our assumption. The delta is really small. Okay. So from this interval, of course, the smallest one is the epsilon over 7. Okay. And suppose the distance, we are bringing back the delta and substitute the delta with the epsilon. So we get this expression. And when we apply, okay, when we apply from here, I will write here, maybe here. So this from here, we can see the x plus 3 is less than 7. Okay. And x minus 3 is less than 1 from here, from this expression. You don't need to write the absolute value actually. So when you have x minus 3 and x plus 3, this is epsilon over 7 multiplied by 7 from this expression, from the right expression here. So because we are choosing our delta is epsilon over 7, then all this will be less than epsilon. So by using delta equal epsilon over 7, we conclude that limit as x approaching 3 of x squared is equaling 9. Then proven that Actually, what you are doing is, in this case, is first assuming any number that really small that for you it's easy to calculate. Okay, and then solve the inequality here. Okay, find any relations between your given number and then your number that makes trouble here, x plus 3 here. It's the same case if you find different factor. If you find different factor, then you need to find the relations. Okay, okay, confused? Confused, right? Confused? Okay, in chapter 2, this section is personally, for me, is also the difficult part to understand. Okay, what is epsilon? What is delta? Here, the epsilon number 7. Yeah. So this is from here, from this expression, because x plus 3 is less than 7. When we are dealing with the x plus 3 here, it should be multiplied by 7. Okay, so first, we imagine, okay, from here, we got the smallest number that possible is epsilon over 7. Okay, we can try that epsilon. Okay, we can try that epsilon. Try that epsilon as our delta, the smallest delta possible from the interval. Okay, and we try to make an equation back to the original one. We try to make the original one. Okay, so we have this. Okay, this equation here, and then we are making a new expression, the x plus 3, and by the expression of x plus 3 here, it's 7. Okay, so this expression here is meant for the from here. Okay, so from the beginning, you see that x minus 3 is equaling something epsilon n over some x plus 3, right? So we need to approach this epsilon over x plus 3 with some assumptions in mind. Okay, so our assumption is we are just making the distance less than 1 so that we can calculate more easily. Okay, we are removing the absolute value, expanding the -1 and 1 here. Try to make the same expressions as this epsilon over x plus 3. Okay, and we get that this is epsilon over 7. Okay, this epsilon over 7 is the smallest possible from our assumption, right? So we are put back the epsilon over 7 as our delta. So we put back here as our delta. Okay, and then we need to bring out the original equations, okay, which is x squared minus 9. So I need to multiply with x plus 3. Okay? X plus 3 in our assumptions, because we already assume that it's less than 1, we need to just to use this 7. Okay, so that's why here we need just to multiply by 7. So epsilon over 7 multiplied by 7 is bring back the epsilon as the original equation, x squared minus 9 less than epsilon. Okay. So what you need to do is, if you find like this kind of situation, epsilon over x, or maybe epsilon multiplied by x, okay? So what you need to do is you need to remove the x, okay? One approach is, for me personally, I think this is one of the easiest way, okay? You can assume with any number. You can assume with any number that you feel small, because when you calculate, you will canceling that number. Okay, intuitively in math, you will canceling that number. Okay, you can use half, 0.2, 0.4, but you will find maybe difficult number to count, right? But at the end of the day, you will canceling the number, and you will find the conclusion still the same. So you can use assuming any number you want, and that is fine in math as long as you can proving at the end of your results. Okay. Yeah, it will be more analysis if you are pursuing in in math, like majoring in math. You will see more problems like this. But in engineering, as far as I can tell, in limit, this is the part that you need to at least briefly understand. That's fine. Okay. Okay, I want to continue to one more session. It's the continuity is not too difficult because I think most of you are quite understand of what continuity means. Okay. 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 So I will draw some graph. So the blue line is the function. So the blue line is the functions here. So I will write this as A. This is L. So limit as x approaching A of fx is of course L from this graph here. Okay. We call this graph removable point or whole. What else? Might be point. Yeah. Okay. But here, limit of x approaching A of f of x is not equal fa. Okay. Okay. From the part here, when you plug in fa, you will have another number. We have another number here, maybe b. Okay. It's not L. Okay. But still, you have limit. Okay. And the second part here, this is we call the jump discontinuity. So all this tree graph is all discontinuous. So this is, if this is A, the limit is doesn't exist here. Okay. Okay, because remember, if you approach from left, approach from right, it has different value. That's why it doesn't exist. Okay. The last part here, we call this is the asymptote discontinuity. We have this is A, or this is x equal A. Okay. X equal A become the vertical line, become the asymptote line. Okay. And limit x approaching A of fx is also doesn't exist because limit of x approaching from right is not the same as limit approaching from left. Okay. So from case number one, from the top one, middle, and then last one, it's all we call this is discontinue or discontinuity. Okay, whenever you have, for example, this point here, whenever you have a hole in your functions, there's a point that is not defined. You may have the limit, L, but because of it is not the same as when you are plug in the number, it's not the same value, we say it's not continue. Okay. So all of this is not continue. This is of course because there's no limit. There's doesn't exist the limit. There's discontinue. The third one also the same case doesn't exist because left hand limit, right hand limit is not equal. Okay, this doesn't exist. Then we may have a formal definition of continuity, okay, which is important when we next dive into derivative. Okay, okay, so this is all discontinued. Okay, so the simplest way to understand the continue, okay, when you graph the functions, your pen is on the paper all the time, right? Meaning it's continue. Whenever you take your pen, it becomes discontinued. Okay, that's the easiest way to understand the logic behind the continuity. For the formal definitions, okay, the formal definition, this is f of x. The formal one is f is continue at, let's say, this is c. At x equals c, if, okay, limit of x approaching c of fx is equal with its value at c. Okay, this is the one that you need to take notes. Okay? This means continuity. This means continue. So if you have this expression, it's true, then your function is continue. And then the questions raised, okay, the questions also raised. Okay. If you see here, okay, I will go here a little bit. Okay, if you see here, if we say all the interval in this graph, the jump discontinuity graph, we may say the limit doesn't exist. Okay, but if we take maybe the intervals from here until here, until this maybe A or not A, maybe B, C. Okay, this part, this interval, it's continue, right? Only on that interval. So we can also have some definitions in some parts of our functions. Maybe it has discontinue. In other parts, maybe it is continue. Okay. So let me let me write continuity over an interval. So for example, if your functions is continue over, let's say, the A to B, okay, this is open interval, okay, meaning we'll write here f is continue over every point in AB. That's easy, right? No problem here. We say also f is continue over, now is the closed interval AB, closed interval. So I will write here, if f continue over closed interval, if f is continuous over every point, this is open interval AB, and then the limit as x approaching a from the right side, okay, is fa. And the third one, if x approaching b from left, is equal fb. Okay. So we say the function is continuous over the closed interval ab is when in every point between the interval ab, the all is continue, and you can prove that the limit at the end of the interval is the same as the when you plug in the number to the functions. Okay, so let me throw some illustration here. So this is A, this is B. Okay. So what does it mean is in every point in the middle of A and B, it's continuous, right? And you can prove that in here, you go from right, so limit of A plus, okay, approaching A from right, okay, is the same as f of A, fa, okay, and the B part here approaching from the left, okay. You need to make sure that the limit is the same as the f of B, for A is the same as f of A, okay. I hope it makes sense, okay. I hope it makes sense, okay. So that we can say function is continuous over the closed interval when you also can prove the limit at each side. Okay. Okay. This is the continuity. I have some examples, but I think I will skip the examples for now. I will go for limits at infinity because I forgot to mention that last week. Okay, any questions so far? Okay. This continuity makes sense. Okay, makes sense, right? Okay. Okay. As long as you have a good sense on this continuity, we can go further for the next chapter of calculus. Okay. Because derivative differentiation is based on the continuity. Okay. Okay. For the precise definition of limit, you may choose not to going too deep. Okay, going learn and understand. You may have some confusion. That's normal. That's normal. That's normal. Later you can review. Okay. I also don't understand what delta epsilon at your age. Don't worry. Okay. So next page is limit at infinity. So if the function defined on, we can say that the limit as x approaching infinity of f of x, we can say it's some number here, L. Okay, so what does it mean is when you have the like this one, maybe it's going further to infinity, and limit of x equal of f of x is, in this case, is the 0, right? Here, the red line here. Okay. This is L. Okay. This L here, or y equal L, is horizontal asymptote. Okay. So before you have the vertical asymptote, now we have the horizontal asymptote. And aside from this limit, we can also make it negatively going left. We can have the x approaching negative infinity of f of x equal L. We can also have this if function defined from negative infinity until a. Okay. Another thing is the limit as x approaching infinity. If you have 1 over x and you have some exponent r, okay, you can make this equal 0. Okay, I hope you also remember. So this is a if r is greater than 0, rational number, and x with the power of r defined for all x. And also the same reason here for the negative limit, negative infinity, is also 0. So these tools, below, okay, the 1 over x with some exponent, you can use this to evaluate limit also. If you have limit, usually in polynomial and in fractions, you can use this limit. Okay. And then you can also have a possibility for example, it can be also infinity, and also at least for at least for possibility. It can also happen. It depends on the functions. For example, okay, let's try some example for this limit. If limit x approaching infinity, okay, based on what we in the previous page before, 1 over x with exponent, what we can do for to solve this problem. Remember? I think high school, right? Remember? Okay. You see it at the top is the biggest polynomial is just this square, right? The down part is on the same, right? At least you have the same, okay, the same degree here. You can divide all by the highest degree of your variable. In this case, squared, right? X squared. So we may say And from the definition before, all these parts having a polynomial exponent in positive number, all can be 0 when you have limit as x approaching infinity. Okay. This all can be 0, and you can conclude 3/5. This is just to remind you all the method you have learned before, I think, in high school. I will go in details, but I don't think we have time now. Actually, for this session, there's one more for the chapter 2, and then we can go chapter 3. I will go next Monday, okay, for the next session. It's called the intermediate value theorem. It's not really that difficult, that complex theorem. I think you have also learned before, but you don't realize what it is. But I think we will go that one, and then next chapter for derivative. Okay. I plan. Okay. My planning. Okay, my planning. We will have quiz in October, but I think it will after the. You have next Friday holiday, right? Next Friday 9 is also holiday. Maybe after next one, maybe around 16, okay, or the Monday, maybe 11 or 16. Okay, I will announce at least 1 week before, okay, when the quiz will be. Okay. The quiz, it's only chapter 1 and chapter 2. Okay, chapter 1 is all about function. Chapter 2 is all about the limit. Okay, the tangent, the velocity problem like the beginning. Infinite limit, limit at the infinity, etc. All the chapter 2. Okay. Yeah, that's it. Just 2 chapters for the quiz. Okay. It will be short quiz. I think I will only prepare a few questions, maybe around 30 minutes. Okay, 30-minute quiz. Okay, I think that is for today. Okay, so thank you for attending the class. If you need the QR code, let me know. I will show you the QR code. Okay, so for online students, for the quiz, I will announce you later how we are going to do the quiz. Okay.